Hi, thank you so much. Yeah, thank you all for coming here today, this morning. I want to say also a big thank you to all the organizers here at the Data Science Conference. This is my first time in Ukraine. I'm super happy to be here, and I'm very impressed by the whole data science community that I've was able to meet both this morning and yesterday too. I'm super excited to meet more of you afterwards as well. So here today, I'm going to tell you a little bit about what I've been working on for the past few years at Salesforce on abstractive summarization using deep learning. I'm going to cover why I think this field is important. Maybe some of you know a little bit about why this is, how it's being used. Also going to cover the challenges that we face right now and different ways that you can draw about this field. A little bit more about me to begin with, to give you a bit of a background on myself. So I've been studying computer science in Paris at a school called ISEP. Maybe you haven't heard of that. It's not a very big school, but taught me lots of cool things about computer science. Then I moved to the US about 6 years ago to work at a small startup called MetaMind, where I worked as a front-end, back-end engineer. We had deep learning as a service platform where we let everyone use their image or text data and then classify it using a platform. And so over there, I was mostly working on the product side. And then in 2016, when we got acquired by Salesforce, I moved on the research side. And that's where I worked mostly on all of the NLP-related things that I'm going to talk about. So to begin with, why is this a field that is worth working on to begin with? Maybe when you think of deep learning or NLP, this is not the first field that you have in mind. But one of the big reasons why we're working on that is because we live in an age with so much information that comes to us. Now the problem is not really finding or having access to information. It's keeping up with the pace of it, both as consumers when we browse through everything we have on our phones or our news or even our chats with our friends. And also companies also need to make sense of all the data they have, mostly text data, regardless of whether it's consumer reviews or internal chats, customer service. All of that needs a way to make sense of it. One big approach that companies have used is a search approach where you take an input from anyone and then try to find the relevant documents from that input. Or you can also have another approach that can also complement it, which is a summarization approach, in where you will not wait for someone's input, but you will, given a whole set of documents, just summarize what are the most important parts of it, either by taking small pieces of it or rewriting different ways what the document means. So how do we go about this? Fortunately, just like many problems today, we have lots of data, so we can apply deep learning. So as I'm going to show later, we have some data that's we can use in supervised ways in some domains, but not always. That's also one challenge I'm going to mention later. So many of you are probably familiar with the basic building blocks of deep learning for natural language processing. This is most in most of the models that have been released in the past 5-6 years. The picture on the left shows a way to do text input-output. So you use recurrent neural networks in that case, which is what is represented by the green and the blue blocks here. You can basically have, if you have a text input, you can decompose that text into tokens, which is usually words. Sometimes it can be subword units. Transform all of these tokens into vectors, and then that gives you an input that you can pass to the recurrent network that will then transform that input into a fixed vector that will be the representation of that input. Once you have that, you can use a second network called the decoder network that is most of the time also an RNN that will then generate your output, in our case, the summaries token by token. This kind of framework of model has been used pretty heavily in lots of other NLP tasks like machine translation or question answering. The one main limitation of this basic model is that if you have long inputs or long outputs, it's pretty hard to condense the whole meaning of the input into one fixed length token. So to compensate that, the model on the right is a variation of that that's also very popular among NLP researchers, which is the sequence-to-sequence model with attention. But this time, when you have the decoder network, the red network here, whenever it wants to generate a new word, it can also look back at arbitrary states of the encoder in blue by the attention mechanism. And that helps create better long-term dependencies between input and output. So for the past few years, most researchers assume that if you want to have a state-of-the-art deep learning model, you will have to use some kind of recurrent network because that's very convenient to deal with variable length units. But increasingly, we've seen the limitations of these, specifically because the bigger the output is, the longer it takes to compute the final state. You have to do the operations in a sequential way every time. So that's why a couple of years ago, some researchers have been trying to go beyond that and forego the iteration step of the encoder completely. And that's how you come up with networks like the transformer network. And instead, they rely heavily on the attention layer that I have showed earlier. So most of the models we're going to talk about are not really using this because I'm going to talk about word that predates the transformer, but just to give you an idea of how fast the field is changing and the different ways you can go about this in the future. So some of the ways these different networks have been used to achieve pretty impressive results on NLP tasks are here. For example, this one in question answering, using actually the transformer network I just showed. Some researchers have been able to beat humans on a question answering task called the Squad 2.0 dataset. For those who don't know, it's a way to frame the question answering model in a way that you have an input paragraph from Wikipedia, a question about that paragraph, and then the task is to predict either whether there is an answer in the paragraph based on the question, and if there is one, which words in the paragraph are the right answer. It's not the only way to do QA, but it's a way that's pretty easy to frame and to train with a very clean data set. And this has been introduced a couple of years ago, I believe. And at the time, there's a significant gap between AI performance and human performance. But then a few months later, with a transformer network called BERT, AI has been able to beat humans significantly. Another breakthrough that I really like, because this one is actually used in production, is the way Google does multilingual translation. They actually use it in production at least in 2016, because that's what they have revealed to the public. I don't know what they do these days, but I'm assuming it's not too far off. Here, it's a variation of the sequence-to-sequence model. And the big difference here compared to previous approaches is that they have a single model for many language pairs at once. What most people used to do before is to train a model for translation based only on one language pair, let's say for French to English. But here what they do is they train that from any language to any other. And the way they can give the target language is just to add an extra token that says, this is the input, and then just translate that to any language that we have. So it doesn't have to be a new model, just a new input instead. Another brief breakthrough that I'm also very excited about, just to give you like more of an idea of the whole field, is unsupervised machine translation. One big issue we have in translation and in summarization too, and I'm going to show later, is that we don't have good data for everything we want to do. For example, for translation, most researchers don't have a lot of data for languages that are not spoken a lot, either online or in the world. And so this is also a way to overcome that and just take language data that is not supervised. We have some in one language, but we don't know the translation yet. So I encourage you to look into that if you're curious, but that's just to give you an idea of what's possible to do in deep learning for NLP. So the question now is, how can we use some of these techniques or some of these building blocks and apply that for summarization? And so before we answer that, I want to give you some of the ways that people in the past 10, 15 years have been trying to solve that summarization problem. One of the earliest ways before neural networks or even machine learning was widely adopted was to use what I will call fit systems. This is basically systems that don't really use a lot of machine learning or sometimes no learning at all, and instead rely on heuristics or expert knowledge or just that simple counting methods like TF-IDF that tries to quantify how important a word is based on how often it appears in that document and compare that on how often it appears in other documents that are not related. And based on such methods, you can derive the importance of whole phrases based on the importance of these words. So the pros is that it is very easy to implement, and it's pretty reliable. You know what to expect from the output most of the time. But it's not very flexible, and it's not the way that humans do summarization. So you will not really get close to a good performance with that. Especially, it doesn't benefit from more data because there is no or little machine learning. And this class of fit system is actually part of a bigger class of extractive summarization approaches in which you will try to learn how important a sentence is most of the time by putting it through a neural network, also having it in context with the whole document and then learning that. And then the summary is going to be comprised of only sentences or phrases from the input document. The advantages is that it's pretty robust. Every phrase from the summary is going to be from the article, so there's a high chance that the facts and the coherence is going to be high, but it's also not going to be as flexible as you want. If you ask humans to summarize something, it's pretty possible that they are going to use new words, new phrases, and that's something that these kinds of systems are not able to do. Which is why the more ambitious approach, the one I've been working on now, Abstractive Summarization, lets the model actually generate summaries word by word and letting them use new phrases and new words if they can to condense the meaning of the document in a very concise and abstract way. And so the advantage, of course, it's the only type of model that will allow us to get human performance, but the advantage is that it's not getting us human performance right now. It has the potential to make a bit more mistakes because it's more flexible. And so we're going to look into what that means in practice with some models. So I'm going to look at what happens if you try to apply the basic sequence-to-sequence models to summarization and how we have dealt with that and made some improvements on that. So one of the main issues if you try to apply summarization using just a simple encoder-decoder model is that if you have a pretty long summary, let's say a few sentences, then you will very often have your model repeating the same phrase a lot of times. And the reason is because these models, the decoder cannot really create long-term dependencies too much. And also because of the way we train it, it's very hard to teach the model what makes a very long summary coherent over the long run. And the fact that the inputs are also pretty long doesn't help either. And for a long time, the summarization problems we've been trying to tackle have been actually pretty short. And it's only when we try to go beyond a summary that's only a sentence long that we come into issues. So one way we have dealt with that issue is through this work that we have done a couple years ago, where we start with the base encoder-decoder model, but we add two things. Here, we use temporal attention, which is a type of attention that actually penalizes the attention weights that have been high in previous steps, which encourages the model to look at different parts of the document to make sure that we cover lots of grounds and we don't forget any important information, but also we don't look at the same parts of the document every time. And another way, which is called self-attention, actually adds more or less the same attention mechanism that we have seen, but this time in the decoder, which allows here the decoder network to look back at arbitrary other decoder steps in the past before computing a whole representation. And once you have these three things, the temporal attention state, the self-attention decoder state, and the decoder hidden state, you can concatenate these, pass them through a softmax layer, and then you can predict the next word of the summary here. Also, something that is not shown in this diagram for simplicity is a pointer mechanism. As you may know, when you want to generate a word through a softmax layer, you need a fixed vocabulary, but you will not be able to get every possible word in a fixed vocabulary. Especially if you have news articles, you will often come across proper nouns or rare words, So we have this extra switch that allows the decoder to just copy words from the encoder, especially when they are rare words or proper nouns. So that gives us some improvements, but there are still ways to do better. And one of the issues actually that also leads to repetitions is the fact that when you train these models, you do it with an algorithm called teacher forcing, which is the most straightforward way to apply gradient descent with a decoded sequence. But it means that the way you train and the way you predict are very different. When you train, you have access to the ground truth words every time, and you have it for like a pretty long sequence of tokens, for like 100 tokens sometimes. But when you predict, you are completely free to predict whatever the model does, and so it can lead on many errors down the line. So to ensure that we learn a coherence of the whole decoded sequence, we add an extra reward to this training thing using reinforcement learning. So RL is a way to train models when you have a loss function that is not differentiable, or also when you have a model that only has a score after many discrete steps. And this corresponds to what we have here. We are generating a whole summary, and then only after that we know whether that summary is pretty good or not. And the reward we're using is actually the same score that we use a lot of times for evaluation. It's called the Rouge score. If some of you know a little bit about machine translation, you may have heard of the Blue score, which compares the phrase overlap between the generated sequence, the ground truth sequence, and Rouge is very similar to that, but more geared towards summarization. And here you can see this is our final loss, where we use the maximum likelihood loss, the teacher forcing loss, and we mix that with the reinforcement learning loss as well, with some mixing factor gamma, to make sure we have both very standard training and then add some of the Rouge score on top of that. And we saw in practice that we indeed have some pretty big improvements compared to previous approaches, which is plus 4.41 Rouge 1 scores on that. And you can see in action the model summarizing word by word input document. On top is the summary. The blue shades are the intra-attention weights on a decoder that I showed earlier. And the green shade is the temporal attention of the encoder, just looking back at different words that are part of the source document. So despite these improvements in Rouge score, there are still some limitations of this model. And the main issue that we have noticed that at first surprised us, but then we realized we were not the only ones experiencing that, is that even though we let the decoder generate pretty much any word it wants, it still very often just copies words from the input document. And we weren't sure why it did that, but then after further observation, it turns out that it's pretty simple. Copying words from the input document is the safest way for the model to ensure that it has a summary that corresponds to the article. The model is not really encouraged to be more abstractive because being abstractive works already pretty well. But the issue is that humans will very often use new words. Like we've looked at the CNN Daily Mail news dataset, and the human summaries use 15% of new words that don't show up in the article. So we're trying to bridge that gap between 0 and 15%. And the way we did this was by modifying the previous model by decomposing the decoder into two entities. We have here this contextual model, which is very similar to the decoder we showed earlier. But beyond that, we also introduce a pre-trained language model, the blue model right here, that is pre-trained on the summaries. And its goal is to try to learn what a summary of our data set should look like. And that way we'll rely more on that generation step and less on copying words of the encoder. And once we have the hidden states, both from the contextual model and from the language model, we use a fusion layer to act as a gating between using the generation from language model or the copying from the contextual model. And then the word generation part works the same. In addition to that, since earlier we had this loss function that allowed us to optimize pretty much any score we want. We introduced an abstraction reward to be combined with our previous reward as well, to give a high score to sequences that use novel sequences of n-grams. And in practice, if we look at the summaries of this model compared to other state-of-the-art models from that time, we can see that it does indeed have a higher rate of higher n-grams, but also more novel phrases. Here in yellow, this indicates words of the summary, sequences of words of the summary of 3 tokens or longer that are just entirely the same as in the source article. And we see that our model, the last one, is able to get a lot more tokens that are not found in the exact same way in the source article, while still having a root score very close to the ones of the previous models. But we've noticed, obviously, that it's pretty hard to improve both the root score and the abstraction. And sometimes it's a bit of a trade-off between having high abstraction, but not having the right words. So to measure that trade-off, we have plotted all the variants of our model with the different additions we've done to it to see whether this was actually giving us a nice boost in both root score and novelty. And as we can see, our final variant, the pink one, is indeed at the top right corner, which means it has the highest trade-off between root scores and novelty of words in the summary. So this is all very promising, but these models are actually not quite ready for production, and there are still lots of work we have to do. But what has been frustrating to me this past year has been to see that the field has been quite stagnant, despite all of the progress that we still have to do before going to production. And when that happens, you have 2 options. Just keep trying new things until you get it working. But if none of the other researchers also get high improvements, maybe you should take a step back and wonder, maybe we are framing this problem in the wrong way. Maybe we should criticize the methods we've been using to train and evaluate, and maybe set a new tone for the whole research field, which is what my colleague Wojtek Krzyżanski has been doing this past year. And recently he published this paper called Neural Text Summarization, a critical evaluation, exactly going deep into what has been the trend in the past few years in summarization and some of the main issues with it. And it goes to 3 parts. The evaluation metrics that we have been using are a bit problematic. The data sets too have some biases that we're going to explore in more detail. And the models as well have a lot to be improved on. But we can start with the metrics to begin with. So earlier I've been talking about the root score, which compares the phrase overlap between inputs, between the generated sequence and the reference sequence. And the reason we use the root score is because when it was introduced in 2004, it has been shown to have quite a good correlation with human judgment on some summarization tasks. But the way we do summarization now is with way bigger sequences, with way more abstractive ways. And that metric now is just way too simple to capture all the complexity that is associated with summaries. When you ask a human, for example, to judge if a summary is correct, they will usually give you 4 points: whether the facts are correct, whether it's relevant, whether it seems like it uses fluent language, and whether the whole summary is coherent, especially if it's a very long one. And what my colleague has seen in that paper, looking at human studies, is that for the current models, the current data we have, there's actually quite a weak correlation between root score and human evaluation right now. And in fact, looking at state-of-the-art models from the literature from the past year, 30% of state-of-the-art outputs have factual consistency issues in the abstractive summarization ones. On top of that, there are some issues with the datasets that we've been using. So far, I've only mentioned the news datasets because that's what we have with the highest amount of parallel data. For example, the CNN Daily Mail dataset that we've been using for our paper has 300,000 pairs of articles and human written summaries, which is a lot to train very, very good models. But the problem with news data is that journalists are trained to write the most newsworthy information towards the beginning of the article, which makes sense and which is something that is a standard journalistic practice. But it means that when we train our models on that, it's not clear whether they're going to generalize to new kinds of data like chats or books or technical documents. So that's something that we can't really address a lot because we don't have a lot of data in these other domains, but it's really important to keep in mind whenever we make improvements on these news data sets. And on top of that, looking at the very specific summaries that humans have written for these data sets, we can see that the task as it is written right now is actually a bit too vague to capture a consistent signal that models can pick up on. And the reason is because at first, the humans will often disagree on what makes a sentence important, which means the disagreement over what the summary, which is abstractive, will look like is even bigger. But one way to fix this is to ask the human annotators to answer questions about the article first, such as here to help them focus themselves more on what the article is about. And once you ask them to answer these questions, they will give you summaries that much more agree with each other, both in terms of words, in terms of conciseness, and of which parts of the article is more important. So using that trick to refocus the field might be helpful in the future to make models that pick up on more signal. And on a related note, if we look at very different kinds of models from the literature for the past couple of years, we can see that they are more similar to each other in terms of outputs than they are similar to the human data, which also confirms that there is something in the human data that models just cannot pick up on, no matter how they are made. So that also should make us realize there is a lot more complexity that some models don't really capture right now. So all of that is pretty exciting to me, even though it seems like it's an admission that nothing works. Actually, it means there is so much more to work on, and the field is like far from being solved. And so that's pretty exciting to me and gives me lots of ideas on things to work on in the future. And besides for these issues, there are also a little bit more challenges when we want to go from research to production models. So I want to go back for a little bit to the issue that I mentioned with having reliable facts. That's a pretty big, both practical and ethical issue for me as well. Because if you deploy such model in the wild and trust it to give you good information, you might end up with people thinking that your summary says something about the article that it doesn't say. And with today's craze about making sure we don't have fake news, it can quickly blow out of proportion. And then researchers are blamed or technical people are blamed. And we don't want that. We want to make sure people can trust our model, can use it safely. And so ensuring the consistency of the summaries is something that's being done more and more in the field. One promising direction to actually get towards that is to use another NLP task called textual entailment. Maybe some of you have heard of it. It's the task of having two sentences or two documents, and then checking whether one sentence is a logical conclusion of another, whether they happen for the same reason, or whether they have nothing to do with each other. So twisting that task a little bit and mixing that with summarization gives us a little bit of boost about the consistency, but there is still a huge gap. I think in one of these two papers that I've shown on screen, there's still maybe more than half of the summaries have consistency issues, but still it's a pretty promising direction that I think is going to be crucial if we want to go to production with these models. Another issue that touches a little bit on what I showed earlier about having bias in the news data is that today, when I was at Salesforce, some customers come and ask me, hey, I've seen your work in summarization. Can you make it work for this? And this happens to be a very long 100 pages document of technical language that I have no idea what it means. They don't give me any parallel data, any reference summaries. They just assume it's going to work. So I wish it did right away. And having models that can either transfer the knowledge from news to other documents, or just having more data in these different kinds of domains is something that is really going to be crucial to deploy this to production. I think the most promising aspect and the most promising of these domains right now is conversations, because we do have more and more data. There are actually a very recent data set of Reddit conversations where when someone writes TLDR, you can safely assume that whatever comes after is a good summary of either the conversation or the post they've made. So we're starting to see more and more of these, and I think it's going to be used in production pretty soon once we have good models with that. And another way to address that issue of transferring the domain is also to look back at what I've mentioned about unsupervised learning. Earlier, I showed you a little bit about people doing unsupervised learning for machine translation. And so the same idea is being applied more and more for summarization too. For example, this model that has been published either last year or this year doesn't use any kind of parallel data for translation, for summarization, but only uses autoencoders to take multiple documents, encode them in a fits token, average their representation, and then decode them in a single document. So it assumes that the summary you want is going to be the same type and size as a single document, but it's still a good way to do, for example, a review summarization for product reviews, where you have many reviews at once and you just want like one that gives you the whole idea. So pushing that towards single document summarization as well as other domains, I think is going to be very promising. And the final way to really push that to production and to really answer the needs of our customers is going to do personalized summaries. And this goes back to the fact that sometimes you want a summary that will be tuned to what the reader already knows, especially for technical documents. It can be depending on their expertise level or what they're actually looking for. And that also goes back to what I said about search. That's one way you can mix search history, a profile about someone, as well as the summarization techniques themselves. So yeah, I hope that all of these has inspired you to look more into the field, maybe even work in the field if you're not already doing that. We also do lots of work in other kinds of NLP, pure ML research, computer vision. If you're interested in all of that and want to work in either Palo Alto or Singapore, please send us a message at this address. Thank you so much.
Thank you very much. And now we have time for a Q&A session. So if you have a question, you just raise your hand and our volunteers help you with the microphone. Okay. The first one guy, this one, yeah.
Recently, Salesforce released a CTRL model for text generation. Can you tell if it can help us in the task of summarization?
I don't remember much of the details of that model because it was done by other people in my team. I don't know, what aspects of the model are you the most interested in, for example?
Well, I'm just curious in general if it can be used, for example, as BERT for summarization or...
Yeah, I think we can get ideas from that because, as you've probably guessed, one of the bigger issues we have with abstractive summarization is making sure that we generate a consistent sentence. So yeah, the CTRL model focuses on that, on the language model side. But yeah, of course, getting ideas from that is totally going to be helpful to generate longer sequences.
Thank you.
Okay, the next one here.
Hi, my name's Andrei. Nice to meet you. My question is about the vocabularies, yeah, or maybe tokenization that you have to do in your task. Do you use some open source vocabularies? Do you build it by yourself? And how many tokens do your vocabulary consist at the moment?
So we just create the vocabulary looking at the training data. We don't use any open source one because all we need is just a list of tokens. We don't need anything fancier with like definitions or anything like that. I think in the models that I've been developing, the size is about 50,000 tokens. But what we've been doing is tokenizing based on words. And I think more and more researchers, especially in the machine translation community, are using subword tokens, which helps reduce the vocabulary size and also makes deeper connections between words. That's something that I've learned trying out next too.
Do your vocabulary contain also an abbreviation, maybe some symbol, numeric codes, or it's just a human words?
It's everything that appears most frequently in news articles. So it can also include these kind of abbreviations. Okay,
and the last question, does your vocabulary consist only of English words, or are you trying to do it like in different languages?
We've been focusing only on English datasets right now, but I think actually one of my colleagues did something where if you do multitask learning, you can combine summarization with translation and see whether you can use the English data and then summarize French things. I forgot how well it works, but I think it's promising direction as well to do some augmentation and transfer.
Thank you.
Yeah, please.
Hi, thank you for your talk. It's Mariana from Grammarly. I have two questions. Question one is about metrics. So I agree with you that Rouge is not the best metric to evaluate abstractive text summarization, although I saw some modifications to Rouge that would include like checking whether the synonyms were generated. So like you taking into account lexicosemantic relations between words, basically, and also like entailment relations and so on. So the question is whether you tried different modifications of Rouge, and whether you know how to automate these metrics that you mentioned for human evaluation, like factuality and relevance and so on.
That's a big question. Like, I wish there was an easy way to automate that. I think it's just, I was showing this to make researchers aware that they have to get used to do human evaluations in a deeper way every time in a way. But there is one paper I've seen like a couple of years ago that was doing human in the loop learning. They were doing it for simulated robotics because the idea was also very similar. You have a robot doing a task, which is very hard to quantify using a metric. But if you ask a human to tell which one is doing better every time at every step or every 1,000 steps, then he can learn to do better at that. So I didn't try that outright because it didn't feel very novel, but I think for production settings, that could be something worth doing.
Mm-hmm. And how about modifications of Rouge?
We'll look into that as well. I haven't looked into that myself. I'm aware that there are some that exist, but I think overall, if you want to game a metric, you will, especially if you have very long summaries. I know what we've tried doing, for example, is to maximize the entailment score of the summaries to ensure that they have a high entailment, which means they have a high factual consistency. But even that didn't really work very well overall.
I see. And the second question is, I know that abstractive summarization models built with deep learning struggle from two main things, like generating ungrammatical sentences or non-fluent sentences, if you may, and generating really short summaries. So not if you, for example, were to summarize a 100-page book, you would want to have a summary that is at least like 3 pages long, not like 3 sentences long, right? So do you have any advice on that, maybe? Both of these.
I guess one way I could see it be done, the most straightforward way, is to have a hybrid approach. Earlier I've talked about extractive versus abstractive, but there has been some work done on doing first an extractive pass over a long document to pick the most relevant part, and then a second model, the abstractive one, would rephrase these and compress them. The cool thing is that we can train this whole model end-to-end with reinforcement learning too. It doesn't have to be like a multi-step thing for training.
Okay, thank you.
Who's next? Please raise your hand only. Yeah.
Thank you. Stevan Rudinac here from the University of Amsterdam. It really touched lots of issues I was also facing during my PhD. I did lots of summarization, but in a visual context, you know. So if you look document understanding conference and text understanding conference, they are arguably epicenters for research on the topic. they were moving slowly from Rouge towards something like pyramid score, you know, like, and then pyramid score also has an issues. You have to hand annotate also information nuggets, if you would like to call it that way. And that's also an issue. First, you have to create this human summaries. You have to annotate it. You need a human in the loop for evaluation, actually. It's more reliable than Rouge, but, well, there are apparent drawbacks. Where do we go from there? Where do we find, or do we actually need to think beyond actually human summaries? Jan LeCun was also talking about this, I would call weakly supervised approaches or no supervision whatsoever. So where do we go from Rouge, pyramid score, and similar matrices?
I mean, as I was saying right now, I think it's still necessary to have a human in the loop, or at least to make researchers aware that they have to have humans, at least at the end, to evaluate different aspects of the summary. And I don't really have the answer right now whether we're going to have like metrics to really tell right away whether we can have like a high coherence, high factual consistency. Even language models, which are supposed to give you a coherence score with a perplexity, aren't perfect in that respect either. So yeah, I wish I had the answer.
Okay, and the last one?
Hi, my question is more related to Salesforce product and your research. How it was originally actually started? Was it like a plan for integrated to some core part of Salesforce CRM, like summarizing some activities or chatters or whatever? Or is it like a part of some bigger, like your Einstein AI system, or how would you look like? Thank you.
That's a very good question. So the thing is that Salesforce is something that we have carried on from MetaMind, is we have a pretty clear division between product and research. And so our goal was actually a very high level goal of having a single model that can solve all of NLP. We realized that all of NLP also includes summarization, so that's why I focused more on that, while other of my colleagues focused on multitask learning and transfer learning. But yeah, of course, we have explored ways that we could apply this to Salesforce product. I've mentioned that the chat conversations, that's something Salesforce has a lot in. So it's not something I'm giving up on completely. That's something that might still happen in the future. But otherwise, other people within Salesforce research also are more geared toward product from day one, depending on how urgent the application is, what's the market need for it, what are the competitors on that. Yeah, it's a hybrid approach.